Hello, stats students. Welcome to section 9.3. So in chapter 9, we're hypothesis testing with two means so far. Next, section 9.3 is still testing the difference between two means, but we're looking at dependent samples. I warned you that section 9.3, we were going to talk about that. So here are some examples of dependent or matched pair. I kind of like that way of saying it. Samples. So we could do something like a before and after, like a pre and post test. The example we're going to do today is running an obstacle course, drinking some kind of fancy energy drink, and then doing the obstacle course again to see the effect of the energy drink. So before and after. We could do duplicate measurements on the same sample, kind of like a pre and post, but it leaves a little bit more room for variation. We could do something like a twin or sibling study. So we're going to assign twins or siblings to different treatment groups. So we're looking at an observational study. And then we're going to test or do whatever it is that we're going to collect our data from. And similarly, we could do a matched sample. And it's similar to a twin or sibling study. Its individuals are matched based on some characteristic, like maybe their age or a medical diagnosis or their gender or something like that. So we're going to kind of match people up, assign them to different groups, and then collect our data from those two different samples. So they're matched samples. So one of the key things in this is that you've always got matched pairs of data. So that's kind of an important thing. So this is samples, and most of them are under 30. So we are going to use the t-table for our critical values, and we're also going to calculate our t-test for our test statistic or test value. So a special t-test for dependent means is used, and it's based on the differences between the values for our matched pairs. So I left a bunch of stuff here for you so that you could kind of think about it as we talk about it. So the first thing is mu sub d. So that's the mean of our differences. So the expected mean of the differences of our matched pairs. Now typically, you know how our H sub O is always mu1 equals mu2. Well, we would expect the means to be nothing, right? Because we'd expect the means to be the same or equal. So that's going to be one of those parts of the formula that's going to fade into a 0. The second bullet is D for difference. So difference is the difference, subtraction, x bar minus x, x1 minus x2. It's the difference of the values of those matched pairs of data. It's each pair, so we've got to do a math problem, a subtraction for each pair of data. D bar, we know x bar is the mean of the sample, right? Well, D bar is the mean of the differences. So to calculate that, it's the sum of our D or differences divided by the number of pairs. So it's just finding the average of the differences. So it's the mean of the differences of the matched pairs, N is the number of pairs of data. So how many pieces of data you have in each sample. S sub D, this one is a large one. This is the standard deviation of the differences. See what I said here. And it's a nice big formula. It looks a lot like our formula when we were calculating standard deviations by hand. It's a giant radical. It's n, our sample size, times the sum of our differences squared. So the differences actually squared, and then we're going to add them up, minus the sum of our differences, and we're going to square that value. That's all over n times n minus 1. Don't forget to take the square root at the end. So we'll do a practice. There is a lot of stuff here, so I don't know if you notice in the notes, we're going to actually make a table. Last but not least, S sub D bar. So that is the standard deviation of our differences. This is our estimated standard error. We can use this in our confidence intervals. It's the margin of error. Okay, so there's a lot there. So I put some stuff on the sides here so that we could talk about this. So we have to do all of these things because here's our formula for our t-test. So we're going to use degree of freedom. T is equal to D bar. which is our average of our differences, minus mu sub d, all over S sub d, the standard deviation of our differences, divided by the square root of n. This guy right here becomes a 0, just like we had the mu1 minus mu2 became a 0 in our previous formulas. So it looks complicated, so we're going to do an example after we talk about our 3 assumptions and make sure that everybody's good. So our assumptions for our t-test. When we've got dependent samples, like always, our samples are random. But they are also dependent. So if we select a sample, our second sample is going to be based on that. Maybe it's the siblings of all of our first set of data or first set of sample people. Maybe it's somebody who matches up to them. Maybe it is the after data for a pre and post test. So we've got dependent data. And last but not least, if our sample size is less than 30, we have to be approximately normal because that's what we use the Z and the T tables for. They are symmetric or normal data. All right, so let's do an example. So we've got lots of stuff. Actually, no, before we do the example, let's talk about our 5 steps. So hypothesis testing, this is the traditional method. If you want to do the p-value method, we definitely can, and we can talk about that in class. So everything's the same except for step 3 just got magnified. So our first step, just like always when we're doing a hypothesis test, identify the hypotheses and the claim. Step 2, find the critical value. We are going to the T table for our critical value. Step 3, compute the test value. So we're going to do that formula that we just got jotted down. But in order to do that formula, looks like this, with D bars and everything else in it, we have to find all those bits and pieces. So here's how the best method to keep track of everything. Some people aren't going to want to make a table. You can or you can't, but you've got to have all this data. The first thing is make a table. Your table starts off with your data set 1 and data set 2, and they're listed next to each other because they're a matched pair. Then find the differences. So here's our differences. We subtract x1 minus x2. We put our answers here in column A, if you like to label it A, and don't forget to do the sum of your differences. Then find the mean of the differences. So we just did, and I know you can finish that table, but remember the mean of the differences is the sum of our differences divided by n. So since you just calculated that, you might as well do yourself a little math problem. I should have written down that that was D bar. So we need that. After you find your mean of your differences, square your differences, the individual ones, and write them in column B. So in other words, if this is a -4, this will be a 16, right? So we're going to square each individual difference for each pair. And then don't forget to find the sum of those squared differences. So that's completing the table. Next up, in order to keep going to get all the stuff we need for that formula, we're going to find the standard deviation of the differences. So the standard deviation of the differences is the giant square root of our sample size times the sum of our d squares. So this value goes right here, minus the sum of our d's, differences squared, all over n times n minus 1. Don't forget to square root when you're finished. Now that we've done all of that, we're actually going to do what it says, compute the test value. So our formula, remember, is this. We jotted that down a moment ago. T equals D bar from step C minus mu sub D, which turns into a 0, all over the standard deviation divided by the square root of n. So we had to do all those steps in order to calculate the bits and pieces. Step 4, everybody knows, make a decision. Again, our decision is either reject H sub O or do not reject H sub O. We never say anything about supporting. We never say anything about H sub 1. And last but not least, the favorite part, summarize the results using the context. So step 3 just exploded. We've got ourselves some work to do. Making a table is really going to organize your information and keep you together and make sure that you know what you're doing along the way. So now let's do an example. Obstacle course time. So this is like one of those pre and post types of things. An obstacle course was set up on a campus and 8 randomly selected volunteers were given a chance to complete it while they're being timed. Then they sampled this fabulous new energy drink and were given the opportunity to run the course again. Their before and after times in seconds are shown. So notice the before and after. So student 1, here's my matched set of data. This is like mu sub 1. I'm sorry. This is like sample 1 and sample 2. Right? So there is our data. So what we're going to do is we're going to pair them up. So is there sufficient evidence at alpha equals 0.05 to conclude that the students did better the second time? Okay, so before we do anything, I'm going to actually write that down again. If this was mu sub 1 and this is mu sub 2, I want you to see where this is coming from. So we want mu sub 1 to be greater, right? They did better, they were faster the second time. So the times for mu sub 1 are greater than mu sub 2, which means if we subtracted that, we subtracted mu sub 2 from both sides, mu sub 1 minus mu sub 2 should be greater than 0. Well, mu sub 1 minus mu sub 2 is the difference of the means. That's mu sub D. So our H sub O, having a trouble writing, is mu sub D is greater than 0. Nope. That's H sub, struggling. Let me try one more time. H sub O is that mu sub D is equal to 0. Right, because we always have the equality. H sub 1, we just said that mu sub D is greater than 0. The differences are greater than 0. I have to do this little side work right here because sometimes I have a hard time figuring out which way the inequality goes. So I have to think to myself, how do they relate to each other, less than or greater than? What would happen if I subtracted the mu 2? Is it going to be a less than or greater than? Critical value, that's going to come from our T table. Because it's a sample of 8 pairs of data. So I'm going to say that my critical value is equal to, it's just going to be a positive because it's a right-tailed test. And I think it's going to be like a 1.895. Check your T table with your degree of freedom of 7. Compute the test value. So the first thing we need to do is make the table. I'm going to hit pause for a second. I'm going to put my data up here just so I don't waste all your time. But I'm going to set up this paired data. So our first set of data is 67 and 68 for student 1. So we're going there. So if I pair up all my data, right, this is student 1, student 2, student 3, before and after times. So I've got my table set up. So now I'm going to do my differences. So I'm going to take each one of these partners, these matched sets, and I'm going to subtract. So 7 minus 68 is -1, 2, 80 minus 86. Oops, that's supposed to be a 76. I was wondering what was going on. That should be a 4, 5. You get the idea, right? So we're subtracting those pairs, and I got to kind of scooch it in here. What's that going to be? 7. While I'm at it, I'm going to take it down here, and I'm going to find the sum of these values. So I'm going to add all these guys up to find the sum, because I need that for finding my standard deviation. I believe it's a 28. Double check me. The negative does make a difference, so watch those signs. So then I'm going to go to, oh, and I should probably, while I'm at it, find my sum, my mean of my differences. So that's going to be something like a 28 divided by my 8 for my sample size. Don't double it. So that's going to be, I think that's 3.5. I like to jot that down on the side. If I'm already there, I might as well divide it out. So then I'm going to do my d squared and put all those guys up there, square all those, and then find the sum of those values. And voila, I've got all my squared values. Remember, when you square a negative, it turns positive. And I believe the sum of those values is 136. So I have, if I go back just to check things out here, I have set up a table. I have found the differences and the sum of them. I did find d bar, the mean of the differences. I did square the differences, put the results in column B, and find the sum of them. So now I need to find the standard deviation of those differences. So this formula right here is going to come in real handy. So let me just put this over on the side. Here's the problem with these, right? They just take up so much space. All right, so I'll put that here, and I'll move this guy up here. All right, so if I'm going to find the standard deviation of my differences, I'm going to have myself a giant radical. Sample size is 8 times the sum of my d squares, so 136, minus the sum of my d's, 28 squared, all over n times n minus 1. Do myself a calculation, check your calculation skills, because remember, sometimes this is the hardest part of it. I got about a 2.33. Verify, make sure I'm on the right track here. Okay, here's the thing. We're not done yet, because we still haven't found our test value. We found all the bits and pieces that we need to do our test value, but we still haven't completed it. So one last formula I'm going to grab, because I don't have it on the same page. Not sure if you do. Don't you wish you could just copy and paste things like that? All right, so here's where I'm going to do a little bit of work. I've got everything I need up here. So my t-test value, I'm actually doing step 3 now. All of that was side math to do step 3. So t is going to be equal to d bar, which we said was 3.5, minus mu sub d, which we know turns into a big old 0, over the standard deviation of our differences. We just calculated that was 2.33. over the square root of our sample size 8. Not so bad once we actually get the numbers to put into the formula. So I believe that comes out to like a 4.304. Again, check my calculation. So right here is the important test calculation. I go to 3 decimal places because my critical value is 3 decimal places. If I've got myself a right-tailed test, and this critical value is 1.895. My test value came out to a 4.304. I am way, way, way in the rejection region, so I'm going to reject H sub O. And my summary would be something like, which one is my claim? Oh, my claim is H sub 1. They did better the second time. And I'm rejecting H sub O, so there is enough evidence to support the claim that the students did better the second time after they drank the fabulous, amazing, wonderful energy drink. All right, so that is what a test looks like. And yes, you need to write step 5, but for the sake of time and your own precious handwriting, I'm going to skip that. So last but not least, the confidence interval for the mean difference. So this is what it looks like. I have a little typo in my notes, so I made sure that I did that. So in the middle is mu sub d. It is the mean of the differences minus our critical value times our S sub d, so our standard deviation over the square root of n. That technically, the S sub d over the square root of n is technically our margin of error, which we wrote in that first page. So this is probably the least complicated, but you did have to do all kinds of work. D bar requires a side math. T of alpha over 2 requires the table. The standard deviation of the differences requires side math. So you had to do a bunch of math on the side in order to get the values you need. When we do this and we check it, this is just like what we've done. If this contains 0, the interval contains 0, it supports do not reject H sub O. So go back and check. We did that in the last 2 lessons with the independent samples as well. If the interval contains 0, it supports do not reject. If there is no 0 in the interval, it supports reject H sub O. We do have one more example, and I know how much you love doing examples, but we'll hold off and we'll talk about this in class. Thanks for hanging in there and have a fabulous day.